Hello pre-calc people, and welcome to your introduction to polar coordinates. So you are used to rectangular coordinates that are measured in XY on a Cartesian coordinate system. And what we're going to introduce you today are polar coordinates, which measure the same distance but in terms of radius and angle measure. All right, so let's look at that relationship. So I start off with a normal, what we used to call our XY coordinate. This is your Cartesian coordinate system. And if I were to locate a point that we used to call XY, I can now look at that same point as a certain distance, as in a radius from the origin, and a certain angle to get to that particular radius, and it corresponds to the same XY coordinate that got me here as well. So we have two ways of identifying the same place. So R is your distance from what we call the pole or the origin, and theta is going to be the angle measured just as a standard angle coming out of the positive x-axis. So because you can see it sort of creates this right triangle, we have a relationship between these. And that relationship is sort of given down here. So we know that x squared plus y squared will equal r squared. So on one side you have your Cartesian x and y, on the other side you have your polar r squared. We also know in relation to our theta, for instance, if I take the cosine of theta, which is the adjacent over the hypotenuse, I can then isolate x, and you get r cosine theta. So that's our relationship between just x and your polar coordinates. I can do the same thing for sine. The sine of theta is opposite over hypotenuse, and then isolating y gives me r sine theta. So there's my relationship for the y coordinate and the polar coordinates. And in terms of theta, we can also do opposite over adjacent equals the tangent of theta. And so we could take an inverse tan to find the actual theta measure. So we're going to be doing some conversions. We're going to be converting from polar, which means you'd be given it in terms of r and theta, to rectangular. So remember that r cosine theta equals x, r sine theta equals y. So that's how we'll do our conversions. You can also then convert from rectangular, meaning you're given the x and the y, to the polar. So r would be this first coordinate, which you get by doing the Pythagorean theorem and then taking the square root, and then doing your inverse tan. Now when you do your inverse tan, remember that you're only going to get a positive answer here. You'll get a negative answer here. So if you want a particular angle that lands in the second or the third quadrant, you are going to have to add 180 degrees. You might also have to add 360 degrees if you want the positive angle in the fourth quadrant. All right, and we'll see how this plays out. Now these first few, and we'll talk about this when we start graphing, but your radius, as before, was always a positive concept. So if you see a negative r, it means you're going to be going like a vector. You would go immediately back 180 degrees in the opposite direction. So that'll come into play on the next page when we start graphing a few of these, but we're going to first focus on converting. So these first few are actually, you don't even need a calculator for this, because we're going to do it on just our normal coordinate. So if I have one negative rad 3, that would put me somewhere down here. So there's 1, here's a negative rad 3. Notice that this is going to be a 30, 60, 90 right triangle, so my hypotenuse would be 2. So when I'm doing my conversions, I know that my radius is going to be 2. And I know that my degrees opposite the rad 3 is going to be a negative 60 degrees. Now, I can write it that way, or I can write it as 2, 300 degrees if I want it with a positive degree. All right. Now, if you don't know your special triangles that well, you may also work this out as, so x squared plus y squared, rad 3 squared, that's going to give me 4, and the square root of 4 is 2. And if you did the inverse tan of negative rad 3 over 1, it would give you a negative 60. All right. Now on this next one, again, I recommend most of these you're going to be able to do just straight up for your special triangles. This one gives me negative 2, 0, which is right here. So if I had to express what angle and what radius that is, well, my radius is going to be 2 because I'm a distance of 2 from the origin. And my degrees, the degrees to get me there, are going to be 180 degrees. And again, you could do your Pythagorean theorem, which of course is going to give you the square root of 4, which is 2, and your inverse tan. But most of these, if it's one of your special triangles, it's actually just easier to use your relationship there. So here I have negative 4, negative 4. So negative 4, negative 4 would look like this. So we know that my hypotenuse will be a 4 rad 2 because this is a 45, 45 triangle. So my radius will be 4 rad 2. And since it is a 45 degree angle in the triangle, that means I'm going to be 180 plus 45, which will give me 225 degrees. If you're not sure about doing that straight off, you could have done, again, x squared plus y squared. You'll get your 4 rad 2. If you did the inverse tan, it's going to give you 45 degrees because it's going to give you an answer in the first quadrant. So you'd have to add 180 degrees to get the 225. All right, this one down here, 0, 4. So 0, 4 is going to be up here. So we can see that the radius, my distance from the pole, is going to be a distance of 4. The degrees to get me there are going to be 90 degrees. And then we have our last one. Now this one you will need a calculator for because it's not one of our special triangles. It is a nice triple though. So we're going to go negative 5, 12. And so this would be our triangle. So this will be a 13, 5, 12, 13, right, triangle. So, or you can do your Pythagorean theorem, 5 squared plus 12 squared. So we know that my radius is going to be 13. In order to figure out my angle, I'm going to go the inverse tan of 12 over a negative 5, and that is going to give you negative 67.4. Notice that is not the angle we want. That gave us something back here, so we add 180 to that. And adding 180 to that will give me, if I round it off, 113 degrees, which seems more like what we want. Okay, so that is going from rectangular to polar. You're basically either doing Pythagorean theorem or an inverse tan, keeping track of which quadrant you're in. Now we're going to go from polar to rectangular, and if you're not going to be using a calculator, then that means your theta will be your special triangle angles, which all of these are. They all come from your unit circle. So remember that this is r, this is theta, and when we do the conversion, it's going to be r cosine theta, r sine theta. So you're basically figuring out the cosine or sine of that particular angle and then multiplying it by the radius. So if we do this step by step, this first one is going to be 6 cosine 150 and 6 sine 150. So 150 has a reference angle of 30. Cosine will be negative in that quadrant. So that's a negative rad 3 over 2. So 6 times a negative rad 3 over 2 gives me negative 3 rad 3 for the x-coordinate. The sine 150 is a positive 1/2, so this is just half of 6, which is going to be 3. So 6 150 translates to negative 3 rad 3, 3, which kind of makes sense. That would put you in the second quadrant. So now we have 4 negative 120. So we're going to have 4 cosine negative 120, which is the same thing as 240, if that makes it easier for you. 4 sine 240. So that puts us in the third quadrant. So cosine of 240 is a negative 1/2, so this will be a negative 2. And sine is going to be a negative rad 3 over 2, so this will be negative 2 rad 3. They should both be negative, so it leaves us in the third quadrant. Okay, then we have negative 360. So we leave that negative there for now. I'll discuss in the next page when we're graphing what that negative does. But basically, you're still doing negative 3 cosine 60, negative 3 sine 60. So this is going to be negative 3 times a half, and negative 3 times rad 3 over 2, and that would be your coordinate. Okay, so let's see. What else do we have here? Negative 8, 0. So negative 8, 0 puts me back here. So again, now we're going to polar. Sorry. This is my polar. Negative 8, 0 degrees. I just did that. Okay. Well, that is where that's going to be. I'm not going to, again, we'll discuss how that negative works on the next page. But let's go ahead and just do our conversions here. So this is negative 8 cosine 0 degrees, negative 8 sine 0 degrees. So cosine of 0 is 1. So this is a negative 8. And this is going to be 0, which actually correlates as a rectangular to what I just graphed. And the last one, 4 negative 45. So we have 4 cosine negative 45 degrees, and 4 sine negative 45 degrees, which puts us in the fourth quadrant, actually. So this is going to be 4, cosine will be positive there, so 4 rad 2 over 2. So that's going to be 2 rad 2. Sine will be negative, so that will be a 2 rad 2. Okay, now that's how we were doing our conversions. A lot of times you're going to just be doing it with your special angles, which is a good reinforcement of that. So hopefully that makes sense. Now we're going to get into graphing. So now you're getting your introduction into what a polar graph actually looks like. Notice it looks like a spider web. Each one of these is 15 degrees apart. So the main ones we will be looking at are sort of the ones that come off of your special triangles. I could go around and mark these up. We have here 180, but I will wait and mark them up as we need them. You can also do it in radian mode as well, which you will need to. So let's look at how you actually graph a point. So here you have some polar coordinates. Realize the first thing they give you is the r, and then you have the theta. So it's up to you how you want to do it. I could go out to a radius of 6, so I'd count 1, 2, 3, 4, 5, 6. So here is 6 out on my spider web. 3 pi over 4 would take me all the way to here. So this is 3 pi over 4, or 135 degrees. That would be the corresponding point that would go with that measure. So what I usually like to do is, well, that's kind of just showing how you would get there. I'm going to kind of do it as a dotted line. The actual point is right there. So this would be the coordinate. I'm going to call this just coordinate A, so we don't get so busy looking. All right. So you could go out to the radius and then just follow the radius around until you find your degree. Another way to do that, So in B, it says negative 120, so at a radius of 2. So what I'm going to do is my negative 120 first, which puts me back here at what is the equivalent of 240. And then I'm just going to count out a radius of 2, which would be right here. So this, I came back negative 120, came out a radius of 2, and I'm going to label that point B. If I want to do negative 445 degrees, notice here my radius is negative. So what I'm going to do is I'm going to find where 445 is, the positive first. So 45 degrees, count out 1, 2, 3, 4. Here's a radius of 4. So what that negative means is 1, 2, 3, I'm going to come backwards, and here is where my final point resides. So out here was the point 445. Negative 4 brings you exactly equivalent to 4, 225. So I'm going to go actually 180 degrees back, or it's like adding 180 degrees to your angle measure. Okay, now we have two double negative. So a negative 3 and a negative 7 pi over 3. The negative on the degree just means the direction you go. So this is pi over 3 is 60, right? So I'm going to come back 60 degrees by 7 times. So that's 420. So it means I'm going to go all the way around once plus another 60. So out at a radius of 3. 1, 2. So here's a radius of 3. It's as if I went all the way around. I came around. I'm going to go another 60. But now I have to go a negative 3, which means I come out to here. There's your final distance, D. Because this is equivalent, when we draw it out, to 3, 120 degrees, or if I kept it in radians, that would be 3, 2 pi over 3. The negative sent me back 180 degrees from where I would have stopped without that negative 3. And then you have a radius of 3. Look, there's no theta. So that means I go out to a radius of 3. I should have chosen a different number. 1, 2, 3. Oh, actually, that last one I went too far. That D, let's come back one. That should have been, it's hard to read that first inner one. Okay, so a radius of 3 just means you're going to draw a circle that is a radius of 3. That's it. So this is just going to be a circle with a radius of 3. And the pole is going to be at the origin. If you see just theta, well, that is going to be, I'm going to do that in green one, that's going to be the equation of a line, and theta equals 60 is going to be your slope. So I come out here to 60 degrees, and in both directions, so it's actually going to, if I can do this right, this is going to just be the equation of a line that has basically a slope of 60 degrees going up and back. All right? So that's how you would just graph a point going around your circle. Now what we want to do is we actually want to convert these. So I want to give you a little refresher on the toolkit that we use for converting. So remember, we had x squared plus y squared equals r squared. So we can utilize that. We have the tangent of theta, that's y over r. And then you also had x equals r cosine theta and y equals r sine theta. So this is your toolkit for doing these conversions. So we have r equals 5, which is the equation of a circle, we know. So the first thing we're going to do is we're going to square both sides, because we want it to go to, in this case, it's going to go to rectangular since it came to us in polar. So what do we know is equivalent to r squared? Well, r squared is going to get replaced with x squared plus y squared. On this side, we keep the 5 squared, and there you have the equation of your circle. So you're always trying to just substitute x and y for r, or somehow get everything, if it comes to you with r and theta, everything should be in x and y. Okay, so this one, r equals 4 cosecant theta. Well, we want all of our polar on one side. So what we're going to do is we're going to rewrite this. This is 4 over sine theta, because cosecant is the reciprocal. So I can multiply both sides by sine theta. And then we have an identity, y equals r sine theta. So this gets switched out for your Cartesian. And there's your, so notice that r equals 4 cosecant theta, as you will, and this is good to pay attention to, will always represent a horizontal line, y equals 4. If it comes to you just as theta, well, what can I do for theta? We know that I'm going to take the tangent of both sides. So I have the tangent of theta equals the tangent of 3 pi over 4. Well, tangent theta is equivalent to just y over x. Tangent of 3 pi over 4 is a -1, so this turns into the equation y equals -x. So again, remember theta equals, and we gave it a slope. Well, here you go. This is the equation of a line with a slope of -1. So now we have r equals 6 cosine theta. This one's going to be a little bit trickier. So what we're going to do, because cosine, we don't want to use a reciprocal property because we don't have anything for secant. So what I'm going to do is I'm going to multiply both sides by r. So on one side I'll have r squared. On the other side I have 6r cosine theta. Now I can do my substitutions. So I multiplied both sides by r, because I can replace r squared with x squared plus y squared, and I can replace my r cosine theta with x. Now, what you will have to do with these is we're going to make you, sorry to say, complete the square on these so that you can see what kind of equation you have. So x squared minus 6x plus blank. And then we're going to have, so we still have plus y squared equals whatever you're adding to both sides. So we're going to add 9 to both sides, half of -6 squared. And this gives me x minus 3 squared plus y squared equals 9. So notice you have the equation of a circle that has been translated. So the center is at 3, 0. It's still off of the x-axis, and that is equivalent to r equals 6 cosine theta. Okay, let's see. Now we're going from rectangular backwards. We're going to go to polar. So we're going to kind of do exactly what we did before, but in reverse. So x squared plus y squared, we can substitute with r squared. Minus y, we can substitute with r sine theta. Okay, I can factor out an r. Well, what I'm going to do is I'm going to set these equal to each other. That was meant to be a 0 on this side. So we know that r squared equals 2r sine theta. And usually we do have a specification that r cannot equal 0, because a radius of 0 is basically just a point, so it's kind of silly to have your r be anything other than anything equal to 0. So that means it's okay to divide both sides by r. So r equals 2 sine theta. Now I have everything in terms of r and theta, and r is isolated, which is just like how you want y isolated to enter on your grapher. And our last one, x equals -4. So we look at this and be like, okay, well, x equals 4, what am I going to do? I use one of my identities. X is equivalent to r cosine theta, but we like to have our r isolated, so I'm going to divide both sides by cosine theta. But then we're going to also just rewrite this using our reciprocal properties. That's equivalent to -4 secant theta. So notice this will also give you the equation of a vertical line, because that's what x equals -4. Okay, there is your introduction to just converting from rectangular to polar, graphing a few points, and translating the points.